Imagine shooting a blockbuster movie on like a $50,000 camera, but the director has to watch the playback. On a TV, you could literally just go out and buy it, Best Buy.
Right, it's a massive gap.
Yeah, and that creates this huge invisible data problem. Welcome to today's deep dive. We're looking at a spec sheet for HDTV Supply for a device called the AJA Hi5-12G.
It's a great piece of gear.
It really is. It's this professional audio and video converter that runs about $1,000. And our mission today is to figure out how massive 4K video signals are translated for standard displays without, losing a single pixel of quality.
I mean, it's a perfect window into the bottlenecks of modern media infrastructure. We're really talking about bridging two completely different engineering philosophies that just, well, they were never designed to talk to each other.
Okay, so let's get into the mechanism here. Because on one side, broadcast engineers have this 12G-SDI signal. And on the other, you just have standard HDMI 2.0B.
Right, and it's not just a simple plug adapter. You have to think of it more like taking a rushing, high-pressure fire hose of raw data and instantly routing it into a beautifully organized multi-lane highway.
Oh, wow, that's quite the analogy. So the HDMI needs the video, the Dolby Atmos audio, and all that HDR metadata to merge perfectly, right?
Yep, all packaged with specific copyright and formatting handshakes. And it has to do all of that without causing a massive traffic jam.
So why go through all this trouble?
Well, the motivation behind tackling that traffic jam really just comes down to budget and accessibility, because professional SDI monitors, the ones that natively speak that firehose language, are incredibly expensive.
They're super highly specialized, right?
Exactly. So by throwing this $1,000 AJA converter into the mix, film crews can use way more cost-effective off-the-shelf HDMI displays, and they can still monitor their uncompressed 4K 60 frame per second workflows.
Wait, but HDMI was designed for living rooms, not Hollywood sound stages. I mean, if we're cramming 12 gigabits of raw video through a standard consumer port every second, something has to give.
You would definitely think so.
Right. So are we losing color depth? Or does repackaging all that data on the fly introduce lag? It seems like it would just bottleneck the entire production.
Well, that is exactly the tension this specific box resolves. It actually doesn't squish the data or introduce any latency.
Wait, no latency at all?
None. The processing power inside actively repackages the data in real time. See, SDI sends data sequentially in these massive raw bursts, but HDMI needs it neatly packetized.
Oh, I see.
Yeah, and this device perfectly preserves the 12-bit color workflows and all the HDR signaling metadata during that whole packetization process.
And what about the audio?
On the audio side, it actively routes up to 8 channels of 24-bit embedded audio straight into the HDMI stream, so everything stays pristine.
But doing that level of constant, computational repacking has to take a physical toll.
Yeah.
I was looking at the specs, and processing all that 4K data draws 11 watts of power.
It does, and that creates a ton of heat.
Exactly. There are no internal fans, so it relies strictly on convection cooling. The manual explicitly warns you that the unit will get very hot to the touch. They actually mandate that you never stack these converters on top of each other.
Yeah, you're essentially running a dedicated microcomputer at maximum capacity, continuously.
So they literally need breathing room.
Right. The heat is just a direct byproduct of doing all that uninterrupted math. They need physical breathing room just to survive the load.
Okay, so we've solved the problem of translating the signal locally. But that introduces a new physical limitation, because standard copper HDMI cables degrade pretty rapidly.
They do, yeah. You start losing packets after just a few dozen feet.
So in a sprawling, massive studio environment, how does this perfectly translated 4K data physically reach a director's monitor that might be 300 feet away across a huge soundstage?
So AJA anticipated that exact spatial problem. That copper HDMI limitation is why there are fiber SFP variations of this device, like the Hi5-12GR receiver.
Fiber SFP, so they use fiber optics instead.
Exactly. These models swap out standard copper inputs for fiber optics. By leveraging light instead of electricity, they can send those massive 4K signals over miles.
Wow, so bypassing the whole copper degradation issue entirely?
Precisely.
Okay, that solves the distance.
Yeah.
But what about the physical hazards of a busy set? I mean, running miles of fragile fiber optic cable around forklifts and heavy lighting rigs sounds incredibly risky.
It is risky, which is why they build in redundancy. These fiber units feature this really clever auto switch over priority setting. The device constantly monitors the incoming light signal.
Oh, so if a cable gets cut, it just knows.
Exactly. If a primary fiber cable gets completely severed, the unit detects the signal drop and instantly jumps to a backup input.
That's amazing.
Yeah, the monitoring never goes dark, and that is critical when every minute of production costs thousands of dollars.
Wow, that makes total sense. So the next time you are sitting on your couch enjoying a flawless, immersive 4K movie, remember the hidden, heat-generating little boxes making that pristine image possible.
Yeah, it's those hidden layers of infrastructure that actually bridge the gap between the camera lens and the screen in your living room.
Absolutely.
Okay.
And I'll leave you with this. If just translating a single 4K video feed requires a dedicated $1,000 processor that gets hot to the touch, imagine the staggering scale of the invisible, heat-generating infrastructure required to broadcast a live, multi-camera global event in Ultra HD.